uh, we want to continue on a pinhole camera model. And to be honest, during the break, I remember that there is something I totally forget to tell you. Uh, my master degree and my PhD was in photogrammetry. Okay, so I think that's something you need to understand. And I love photogrammetry ever since I graduated. I love photogrammetry. I did my master and PhD in photogrammetry. That's why I'm so excited. That's why I want you guys to get involved. So this camera model here, I doubt that this is new. This is the idea of the camera. And although the cameras right now gets so complicated, but it's as simple as that. It's a black box. Okay, so there is a black box here, closed, no lights get in. And at the back of the black box, we need to receive our image. And that's why in the old era, we have a film, and this film is placed here at the back of our camera and ready to record our image. Right now, we have digital camera. So the digital camera doesn't have a film really. It has a sensitive array of small cells that they can sense the light and simply create a signal in proportional to the light amount of light that they hit them. So that's why it's called CCD, or even we have a new technology called CMOS. Doesn't matter what's the name, but there is a recording media here, a recording media. And at the front, we have here a small, very small opening called aperture. And this aperture is simply opens for a very small time to allow amount of light to get in. And this is controlled by something called a shutter. So the shutter, it opens and closes, and that's why you get your image. There are some electrical shutter and there is some mechanical shutter. So the mechanical shutter, it really physically open and close to allow certain amount of light. But there is also electrical shutter, which is simply something that will stop the signal. Remember, those CCD arrays are creating a signal, and electrical shutter is simply a circuit that stops the signal. But here is how you take an image. So we have a light source. In most cases, it's the sun. So the light source will simply illuminate your object, and the energy or the light will simply reflect back in a sort of light bundle. And the light bundle will go into the this closed box to record your image. This is the some called the pinhole camera model. Okay. Now here is what this is what happens during the photography. So a light will hit the object, then the energy will be reflected, go through the aperture, and then projected on the film plane. Now, I'm asking you right now, what is photogrammetry? So photogrammetry is simply trying to reverse the process. So I'm going to hide. So in photogrammetry, we don't have an object. We simply have the image, and we want to create our object back. You can see the problem here has a little problem because simply we lose the scale. Okay. For example, you can see I have a point here, and this point is on the image. So we have a point here on the image. Let's say this point here, which is the base of my tree. And the best you can do is you can draw this line here, but your point can be anywhere on this line, can be anywhere. We don't know exactly where this point on the line. We lose one dimension. We lose the scale. And that's something we can simply figure out when if you have two images. But this is something you will learn later in my class. Now, something very, very important. I can tell you, some of you probably think that map is an image. An image is in a map. Okay? And so let me see how many of you thinks that map and image, those are the same thing. Map, image, map, image. If you think that the map and image, they are the same thing, show me your hand, please. So the good news is nobody, oh, you think that the map and image, they are the same. Okay, it's not a problem. I'll convince you they are not the same. Watch my screen, please. So you can see here on the left, there is something called map. And really what map is simply, here is my map and here is the reality. So that's the reality. And what we do is we simply project the reality into the map. And the projection here is orthogonal. It means all those projection lines, they go perpendicular to the surface of the map. The only difference is that our only difficulty is you can see here the map size is the same as the reality, which is something we cannot do. We cannot have a 2 kilometer by 2 kilometer piece of paper. And so that's why we simply do something smart. As we simply create our map, we scale down, but it's the same scale. Huh? So if I tell you a scale of 1 to 1000, it means I shrunk my reality by 1,000, ratio of 1,000. And to go from map to reality, we simply have to use the opposite of the scale. So we simply have to multiply everything by 1,000 to get the dimensions in reality. But the thing is here, it's orthogonal projection. Now, when we shift ourselves to our image, let me ask you, look, this is how the image is created. And as I said, the light will hit the object, the reality. The light rays, this bundle here will go to the perspective center of the lens here. And then finally, all the light rays will hit the image plane where your image is recorded. Now, what do we call this kind of projection? Call it perspective projection, because everything goes through one point, or sometimes called projective projection. So all the light rays, all the light bundles will go to the same point, which is the perspective center of the lens. And so this will create a problem. Okay, now I'll say the problem and then I will show you more details. So this one here on the map, we have only one scale, which means if I have a scale 1 to 1000, it means everywhere on the map, the scale applies. If you measure on the top left corner, the bottom right corner, the scale is the same all over the map. For the image, doesn't have the same thing. The image simply, it doesn't have a uniform scale. If you don't follow, then please be patient. I'll prove it for you. Also, on the image, there is nothing called the relief displacement. On the image, we have a relief displacement. In the next few slides, you will know more about this one. Let's prove it for you. So when we talk about the scale, as usual, the scale is the ratio between a distance on my map to a distance on reality. And the same concept applies for image. If I zoom in here, then the scale will be the distance on the image. For example, let's say from here to point C, let's say this is the distance on the image, and the distance on reality is from point C to here. Okay, so there is a ratio in between those guys. Okay, however, the thing is the ratio is not constant. So if you divide this distance by this distance, you'll get one ratio. And if you apply the same concept on point B or A, you will get a different ratio. Watch this. So here I have a demo for you to prove my concept. Look at this. So this is, do you know who is this in the picture? By the way, so do you know who is this guy in the picture?
Tahir.
Yes, that's me when I was in Egypt. I love Egypt. I was in Egypt 2 years ago, and unfortunately, I didn't go to Egypt last year. But that's me 2 years ago. And you can see Tahir is standing next to the pyramid. Which one is bigger, you think? The pyramid or Tahir?
Tahir.
Oh, yeah, sure. Yeah, I am. Okay, but you can see I am taller than the pyramid. But the reality is the pyramid, in fact, is 134 meters above the ground. So you can see it's too tall. Why? Why I'm looking at this picture and I look bigger than the pyramid or taller than the pyramid? Is because I stand close to the image, while the pyramid is very far from the camera. Okay? One more thing. Which one you think I'm me or my ancestor, huh? Which one is bigger, me or them? You can see we're almost the same height here. And I'm a little bit closer to the camera. So you know what? They are bigger than me for sure. This is another example. You can see here I'm standing next to a statue where looks like we're almost the same height. Now watch this. This is myself in Vancouver. There is this such nice building that has this globe hanging from the roof. Which one you think is bigger, me or the globe? Again, if I'm bigger than the pyramid, you think I'm bigger than the globe? Appreciate that. Thank you. Okay, anyway, guys, you probably get it by now that really the image are deceiving. So things are the image doesn't show at the right scale. Things which is closer to the image will look bigger to the camera, and things far from the camera will look smaller. And this is proof my idea. So the idea here is that we don't have uniform scale. In a map, doesn't apply. In the map, if you say something is bigger than other things, it means in reality, this thing is better than other things, okay? Which doesn't apply in image. Another thing called relief displacement. Relief displacement, which is, you know what? I will try to make it easy. I'll just skip some slides because this shows you the idea of the relief on a sketch, but probably it's easier to see it on an image, okay? Now, please look at my screen. In my screen, there are two buildings, okay? And we're looking from the above, from top. Now, I'm asking you, if you see those buildings on a map, do you think we will get the same view? What's the difference if I see those buildings on a map and I see them on an image? You guys figure out what's the problem here? Anybody to see what's the problem? So here is the problem. And let me ask you, if you have a building on reality and you place this on a map, what is the relationship between the top and the bottom? How the vertical lines will show on a map. If you don't follow, then I'm going to show you here. I'll go back to my sketch here, and here is where I define my map. Look at this, please. So if I have a building, here, like let's say this is an elevation, so we have a building here, okay? So I'm asking you, because of my projection is orthogonal, what is the relationship between the top of the building and the bottom of the building? Do they come on top of each other?
Yes, directly over top of
Yes.
each other.
Do we see the sides of the building in a map? Assuming that the sides are vertical,
No.
we don't see them. So let me show you here on an image. On an image, what do you see? Do you see the top and the bottom? Yes. Are they shifted? Yes. You can see here is the bottom. I can draw some lines for you. Here is some line. So that's the top. So this is, yeah, here we go. So this guy here is the top of your building from here to there, to there, to there, and then close it. So that's the top, and I'll give it different color. Okay, that's the top. While the bottom of the building is simply, it's over there. I will simply draw few lines. So this is simply the bottom of the building. Oh my God. So which means the top and the bottom in the image, they are not same thing. They are shifted from each other. You know what? This shift is called relief displacement. And I'm going to clean my slide, and then I will show you what is the relief displacement. Simply, the relief displacement is simply this line here. This line here is the relief displacement. So what does it mean in plain English? It means things are shifted. In an image, things are shifted. Why they are shifted? Because of the relief. If they go up, like you remember, the top of the building is above the bottom, so when we go up in the object space, simply we are pushed outward because of the projective or the perspective projection. This is really what I wanted to know, that the map is not an image is not a map. A map is orthogonal projection, it has uniform scale, and it has no relief. While the image has a perspective projection, it has not a single scale. So every point on the image has different scale depending on how far the object from the camera, and also the image, it has a relief displacement. So this makes my image completely different from a map. And here is one big misconcept. Some of you probably, before you learn this in my class, will say, okay, you know what? We can simply use an image to create a map. How? We can insert this image on AutoCAD. We can do that for sure. And then we can go on AutoCAD, and I will do the same thing. In AutoCAD, I can draw lines. So I'm going to go here, and I draw my line here, and then to this point, and to this point, and to this point. That's okay. Here is my here is my my building. So that's building number 1. I can simply mark it and give it a color, and also I can go ahead and I can digitize building number 2, like so, like so, like so, like so. Now I'm asking you, do you think right now this is right? Like all I have to do is, can I do that? Can I insert my image, my aerial image into AutoCAD, and I start drawing my map by simply digitizing features on the image? What do you think after this discussion?
No.
That is completely wrong. Why completely wrong? Because simply things are not showing on the right location on an image, because you can see they are shifted outward depending on the elevation. So the higher you go, those things will go even worse. You will have more relief, more relief. Okay, now watch this. So I'm going to discuss with you guys something called orthophoto. And before we go into the orthophoto, like the details, let me show you what does it mean, orthophoto. So I'm simply here putting the orthophoto and a photo. Remember, photo and orthophoto. So the one on the left, which one you think? This one here is what? Is that orthophoto or a photo? An image taken by a camera. Which one you think is taken by a camera?
The left.
The left, yes, true. Why is that? Because you can see, obviously, we have our relief here. This is the relief displacement, okay? So it is distorted. The top is simply pushed outward because of the elevation. So that's called an image, perspective image. So what happens here, using some algorithm and software, we can remove these distortions. So think about the relief as distortion. Think about relief as distortion. So what happens if I'm able to remove the distortion because of the height and bring features back to the original location? And that's exactly what I'm doing here. So we went from the perspective image on the left to this product here on the right. So I'm asking you right now, do you see any relief on the right?
No.
No, so there is no relief, and that's why the one on the right called orthophoto. And the surprise is you cannot, listen to this please, you cannot capture an orthophoto using your camera. That's something that this is not natural product. This product here is just processed using a software. So we simply start from the one on the left, we remove distortion, we remove the relief, we are able to generate this one. So the one on the right is relief free. It doesn't have any relief. And that's why it's called orthophoto. Now, let me ask you one more time. Can I insert this orthophoto into my AutoCAD and I start drawing things like the building? Here is my building. Okay. Here is my building. Can I do that in orthophoto? Can I do that?
Yes, I think so.
Yes, you can do that, because right now, after removing the relief, we get our orthophoto and things are in the right location. So the orthophoto is equivalent to the map. Orthophoto is equivalent to the map. So you can see here there is some discussion about orthophoto. It's orthogonal projection. It has uniform scale. It has no relief, and it provides those advantages for users. Okay, now, one more time, I'm just trying to show you the difference between a perspective image and orthophoto. Let me ask you here, if the red line work is a map, which one you think is a photo, perspective image, and which one is an ortho image? The left or the right? Please unmute yourself and tell me, okay? If the red lines, those are map, okay, overlaid on top an orthophoto and overlaid on top of a perspective image. I'm asking you, which one is perspective, the left or the right?
Left.
The left, you can see, look at this. I'm going to zoom in and you'll see that. When you overlay a map, correct map on top of a perspective image, they don't agree, because there are some distortion depending on the height. However, if you overlay a map on top of an ortho photo, then you can see the center line of the road, they just agree. Okay, anyway, so let me test you. What do you think? Is that an ortho photo or perspective image?
Perspective.
Okay, here is the key. As soon as you see the size of the building, it means you are looking at a perspective image. It simply shows you the size, the side of the building because you have a relief. How about this one here for the same area?
Ortho.
This is ortho. Okay, so I want to say something, and hopefully I'm not confusing you. In general, ortho photo is something that it cannot be captured by a camera. It has to be processed. So we take our perspective image, we do some algorithm where we can distort back our features to the right location, kind of removing our relief displacement, so we get an ortho photo. There's only one case, which I'm hoping that I'm not going to confuse you, that you can get an ortho photo with a camera. An ortho photo with a camera. There's only one case, and this case is only for satellite image. Satellite image. If you place your camera in infinity, like very, 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 very far from the object, in this case, you will get an ortho photo. Okay? But in general, if you have an aerial image taken by a drone like this one here, it will not be an ortho photo. Okay, now let's talk a little bit about sensors. You guys, what is my gear here in photogrammetry? What I'm using to create my 3D model? Am I using total station or GPS or laser scanner? What is my gear? What is my equipment? My equipment is, excuse me?
Drone.
No, I'm talking about the sensor. So the drone is just a platform. It just you can attach a camera to your drone and you fly it. So to be honest, the drone is not a gear. The drone is just a platform for me. Just like the tripod of total station, it's just something you set your total station on top of it. But really, my gear is simply a camera. Now the question is, what kind of camera that I can use to create a 3D model? Here is a variety of cameras and options you can use. We start here. So those cameras here are cameras, a digital camera that you can buy off the shelf, okay? And those ones here, they can be maybe 50 megabyte resolution. Right now, there are some amazing cameras available in the market. They're kind of expensive, not cheap. They are probably $3,000 or $4,000, okay? So those are available. Now, on the other extreme, we use something called aerial camera. So those are handheld. We can put them on a tripod or handheld, and we can get amazing photos. Now, aerial cameras are bigger. Because remember, we need to get a better resolution, so they are bigger. And here we have two extremes. We have this camera here, and this is aerial digital camera, aerial digital, okay? So it produces for me a digital image, okay? This camera, it is called Zeiss RMK. And this one here is called Leica RC30. It's an old camera. And this one here is analog camera. And what does it mean, analog camera? Anybody remind me what does it mean, analog camera?
They use film.
Yes, sir. So they use film. But the thing is, the film in your camera, the normal one that probably you own, I think it's 1.5 inches. Anybody can correct me? The width of your film is 1.5 inches, like 38 mil. Is that right?
Yeah.
Okay, so you know what's the size of the format of this aerial camera here? It is simply 9 inches by 9 inches. So the format, the size of your film is 9 inches by 9 inches. Okay. You know what? I know some of you will say, okay, you know what? This is obsolete. You know, in 2020, we shouldn't use any analog camera. Anybody agrees or disagree? Why in 2020 we should use an analog camera while it's completely inconvenient? Because simply you will have to develop your film chemically, and it takes more time and it takes more effort. While the digital camera, right away, it gives you a digital image. Any thoughts? Anyone can guess why are we still using analog cameras while digital cameras are more convenient? It's not easy question, by the way. That's very tricky question.
It's quality.
Yes, yes. Well, I know quality is kind of a vague word, but I'm just gonna assume that you're talking about resolution, okay? Which means the size of your pixel. So the analog cameras, they have higher resolution because simply if you know about photography and try to understand how the film is recorded, the thing is we have a sensitive material to the light, and we simply painted the face of the film with this sensitive material, and that's how we record. So the size of those particles, they are so small. They are 1 or 2 microns. Until now, we cannot fabricate a CCD with 1 or 2 microns size. So that's why analog camera, until now, they are superior in resolution. Anyway, I'll leave it at this point. I'll continue. So just want to quickly share with you guys the history of photogrammetry. We kind of touched on it, but we never went deep into photogrammetry, like the history. How the photogrammetry evolved over the years from 170 years ago until now. By the way, what you have right now is the end. Like, you know, we are almost at the end of it. So we are really very advanced. We have very good product, but things never started this way. Okay, so I can tell you some evolvement of the photogrammetry over time, and I kind of color them in red. So we started here from B, analog photogrammetry, which you guys look at the name, analog. It means we take assembly analog camera, we get a negative, and how we do that? We simply place the negative on a projector. Look at the name, look at the name. So we hang the negatives on a projector, and we light the projector. So when we light the projector, what it creates simply a bundle of rays. Same as this. I'm going to go back a little bit to remind you. Same as the camera model. So we take this thing here, this here, and we take our negative, and we put light at the back of your image, at the back of the negative. So this will create kind of bundle of rays. And what happens is we simply, when we start, the bundle of rays will be hazy because we have more than one image. And when you look at your projected surface, you will see kind of double image, not only one image, 2 images. And then what happens is we keep moving the projective, the images in a way that simply return the situation to where it was when we take the photos. Like we rotate things and shift things until we create our 3D model. Okay, and then from there we can simply digitize our 3D model. Okay, if you don't follow 100% what I'm saying, you know what, never mind. So this goes from 1900 to 1950. 1950 here, it's kind of, you know, it's not really a rough number, like fixed number. It's around this time, around 1950. So we use photogrammetry in analog way for about 50 years. Around World War II, this brought lots of advancement for photogrammetry. Can you guys know why? I already said it. Why? What is the relationship between war and photogrammetry?
The planes came out now and they started. I don't
Excuse
know.
me, sir?
Like planes and stuff, they started using it to map out.
Exactly. That's one thing. But the other thing is, I said it already, you cannot just, you're fighting with someone. And so you need maps for them, for their area. You need where they hide, you know, because if you know map, if you say map, it means I know location, I know XYZ. So simply, I can simply hit them. So photogrammetry and World War II, they were best friends. I can tell you German brought a lot of innovation for photogrammetry during the World War II. Analytic photogrammetry started around this time where things not really analog, we turn things into mathematics. So we turn everything into equations and we solve equation together to simply create our 3D model. And by the way, it's not only about like war and only about inventing aeroplanes, but also about computer. Did you guys know when computer invented? Around what time? Around the same time, around 1950s. So we have around 1950s, we have already computer that can do calculation very, very faster, or at least faster than us. Okay, so that's where analytic photogrammetry started. The word analytic, it means we're not really moving our projector to move our images. Everything, it became calculation. So we create some equations, we solve them together, and we find X, Y, Z of my object. Starting in the year of 2000, things are shifting. Why they are shifting? Here, those things. And those new, I'm not going to repeat myself again. We already discussed what happens from year 2000 until now. You can read them on your own time. Three things, faster computers, development in computer vision, and then finally, high resolution cameras and drones. Okay? So if you are interested to know exactly what's the history of photogrammetry, we have a 36-page, which is available here in this link, to tell you what is the evolution of photogrammetry over the last 200 years. Okay, you can take a look if you wish. Now, here is how photogrammetry works. So photogrammetry is simply requires two images. And why? Why do we need two images? Why is that? Why do we need two images? Why one image is not enough? Can anybody tell me why one image is not enough?
To compare
Okay.
So perspective.
Excuse me?
It doesn't show, like one image doesn't show perspective as well. When you put in two, you can get perspective.
Okay, I'll try to explain. I know it's not easy, so I'll try to explain. But I'm going to ask you one question probably you never asked yourself about this question. Did you ever ask yourself, why do I have two eyes, not only one eye? Anybody thought this way in your leisure time, midnight, before the midterm exam?
Isn't that just depth perception?
Yes, sir. So without two eyes, you cannot see in 3D. The word of depth, it means I see the third dimension perpendicular to you. You can estimate how far things and how close is by having two eyes. And photogrammetry works exactly the same way. Okay, we need two cameras. And I'll show you what does this mean if you don't follow, if you never ask yourself why I don't have two eyes. I will show you what this means in photogrammetry. So, okay, so watch this, please. So here you can see I have my sleeping lion. Good news, he's sleeping, Sleeping lion. I took two images and I'm asking you, those two images are from the same location or not from the same location? What do you think?
Different.
They are from different location. And what happens here is that, every image, remember, I'm talking about image, not space, I'm about the image. So you can create an image coordinate system marked by the yellow lines. You see those yellow lines? I'm trying to create an image coordinate system, okay, in yellow. So every point, it has coordinates. If I zoom in here, for example, this point on the line, we can measure the X and Y with respect to this coordinate system. It's very simple, So you take a piece of paper, you split it, you put all your origin in the middle, you put your X and Y, and you measure this point. Here is my X, here is my Y. Remember, this is X and Y of the point on the right image. How about this? Let's look at here. So we can see here, when I look at the left image, I can also measure the little X and little Y, and those are image measurement on the image. I'm asking you guys, are those the coordinates that we learned in my class, like we can survey by total station? Yes or no? I'm talking about coordinates right now. Those little X and little Y in green, are those object coordinates? Like the one that we use measured using total station, or those are something different?
Something different.
Yeah, those are measured on the image. So the image is somewhere, and we just measure where is this point on the image. Okay. Now let me ask you, what is the best you can do if you know where is the point on the image? Here we go. Look at this. So here is your left image. So this is your left image, and this is your right image. And remember, where is my point on the image? I can see it on the image. I can see this point on the image. Here is the point on the left image, and here is the same point on the right image. The best you can do is you can, I'm going to say it graphically, but things will turn into math somehow. So graphically, you can connect the perspective center to the point on the image, like a light ray, yeah, light ray. And you can extend this blue line in the space in a red line. And let me ask you, what if we hide the right image? I have only one image. Let's hide the right image. I have the left image only. Okay, look at this. So I have a point here on I can see it on the image. Graphically, I'm going to connect from the perspective center to the point on the image and extend my line, the red one. The question is, where is my point in space? So it can be here or there or anywhere on the line. I will just draw the line for you. So my line goes from here and it goes this way. Yeah, this way. I will just try give it a different line type. So this is my line on which my point should be. I don't know exactly where. The only way I can find where is my point is by having another image. And we can repeat the same thing. I can see my point on the right image, like the blue dot. I can connect my perspective center to the blue dot. I came up with a line. Those two lines, if I extend them somewhere, they are going to meet. Where they're going to meet? So they're going to meet here. And this point here is your object point. And this point here, I can find my capital X. I'm going to write it here clearly. So this is capital X, capital Y, capital Z. So those are object coordinates in meter. So what are the other small x, small y? Those are image coordinates. I will try to put them in the same. So here is my image, and I do have here I split my image into 4 quadrants, and I can measure the x and y of the image, of the point on the image, like I did here. I'm not sure if you guys following. So the point here is that I need 2 images. Every image will give me a light ray, and the intersection of the light ray in space will locate the point. So with one image, to be honest, I cannot do anything because my point can be anywhere on the line. When I capture another image to cover the same area, so it means I have an overlapping image, then I can build my 3D. And that's exactly what your brain and what your eye is doing. You have 2 eyes, so you capture a left image with your left eye, you capture a right image with your right eye, and your brain will kind of estimate how far things and how close things. Are you guys following?
Yes.
Yes.
So let's put one rule. One rule. The one rule is here. The one rule is here. It means to find the golden rule is here for photogrammetry. I'm gonna box it for you. Okay. To find the XYZ ground coordinates of a feature point, any point must appear in at least 2 images. So one image is not enough. One image is not sufficient to build our 3D model. Remember, when I say that my feature needs to show in 2 points, looks like I'm looking at overlapping images. Do you guys agree? If I want to find XYZ, I need to take 2 photos, but those photos are not random photos. Okay, those photos must overlap. You can see here, when I say overlap, I mean you can see the left image is showing you the lion, and the right image was also showing you same area one more time. What does it mean? It means I have an overlapping photos. Okay. Now, this exercise here, I will not do it today because simply we don't have enough time. And so, I'm going to give you a little bit of history of last year. Last year, I had some trouble. I've been in the hunt for a software for my students for the last few years. I would like to give them a free software that they can use and exercise photogrammetry themselves. And that's fun. By the way, I myself, do it, very frequently. To the point that I let my daughter sit down and I took 100 photos of my daughter and then I create a 3D model for her. Okay, I'm crazy. Now, last year we used a Meshroom, and Meshroom is a free of charge software that you can download the links that I give to you. However, this year I will not go this way because we had trouble running the Meshroom. Okay, and Just to give you a little bit of background why we had trouble to run the software. The software simply designed on barrel processing. I'm gonna go now right now. I'll go to IT. I'm gonna speak like about computers. Any of you learn about barrel processing? Barrel processing? Maybe not. Maybe not. But you will be surprised. Anyone here in this class is a gamer, like plays video game? No? Amazing. I don't think you guys, you're lying. Anyone here in the class is a gamer, like plays video game? You have to admit to me.
Ryan.
Okay. So please, okay, if you play video games, I'm asking you, do you use normal computer? Like, does it help you? Guys, I need someone. I need to demonstrate that for you.
It needs a graphic one.
See, it needs a graphic card. And can anybody tell me what's the difference? Why the gaming needs a good graphic card that called GPU, like a graphic card? I'll tell you the secret. I'll tell you the secret. So the secret is, when you play video games, the software will need to re-render the scene. Remember, you're running, you're holding the gun, you're playing Viva, okay? So things are changing very quickly, right? And the software must cope up with all this. And that's a lot of calculation that you never even ever think about it. You just enjoy. But you never thought about what's going on your computer. Computer can show you that somebody's running, or you render something. The software will need to do millions and millions of calculations. So how you do it? You can do it either by serial processing. It means you do one calculation, then it's followed by another one, followed by another one, by another one. Or you can do it as parallel calculations. So you can send all the calculation to a processor, and simply they can work parallel. They don't have to wait for each other, and they can give you the results back. Which one is required for gaming? What do you think? Series or parallel? Hello.
Parallel.
Parallel processing, that's really what we need. We need parallel processing because we want to get a very fast answer. And if we have so many processors, then all of them, they can work on the same time and give me my answer. There are some stuff in computation, it must goes on a series because the next result is based on the previous result. But there are so many applications where the next result is not function of the previous results. For example, I want to render 1 million point. 1 million point. I'm going to send my 1 million point to 1 million processor, and they can respond to me. The computation of the second point is not connected to the computation of the first point. So you can see they are not connected. So I can do parallel processing. Okay, why I'm giving you this hard time talking about computer and gaming is because simply the software mushroom is designed to do parallel processing. So it needs a graphic card called GPU. And this GPU, it works by parallel processing, and that's why it's very fast, which the hardware, like the laptop of SATE, doesn't have this graphic card. And that's why the software will simply come at one point and stop. And we have hard time. We have a go around, but to be honest, I decided not to go this way. I decided to avoid this way and go different way. So what I decided is to go and use this software here. It is called Zephyr. If I say it right, Zephyr. And the software here in general is not free. So the software is not free. The software you have to pay. But the good news is the company provides a free complete version. Not for student. It is only limited version where it puts some limits. It says, okay, you know what? You can use my software, but you can process maximum of 50 photos. Maximum 50 photos. Okay, which is in industry, I promise you, you will process way more than 50 photos, way more than that, 1,000, 2,000 images. So that's why the software can be used in my class. I can simply use it in my class, and the maximum is 50 photos, and that's what we will do. Please, everyone, please do the following. go to the to my D2L, go to the content, and there are some material. Probably you can download all of them right now. 1, 2, 3. So we will have 3 presentation in photogrammetry, and you can see here I provide you some called Zephyr tutorial. So if you look at this file here, I provide you the tutorial, and so the tutorial is here, and it tells you how to download the software. Please, between now and next class on Monday, I want everyone, you can see it's on the very top, please use this link to download and install the software, because sometime on Monday, I will do some quick training on this software, okay? And if you are interested, you can just simply read the tutorial. I prepared it yesterday, which takes you to the process on how we build our 3D model. Any questions so far about photogrammetry? Did you fall in love with photogrammetry? If you fall in love with photogrammetry, show your hands. I just love this scene. Thank you so much. Thank you so much. We'll see you guys on Monday. Thank you so much and have a good weekend.
Thank you.
Thanks, you too.
Thank you much. Thank you so much. Bye-bye.
Thank you.
Thank you.